Hi, my name is David.
I'm Jenifer.
And we are part of the UT Math ALEKS support team. And we're talking today about the June 16th problem of the day. And this is it. If this is the question, if this is not the video or the question that you're seeking help for, then this is not the video for you. So we're going to begin by the questions actually asking us to determine the vertical asymptotes of the function. Well, first we should tell you that the actual function is a rational function. A rational function is defined as the division between polynomials. And so if you look here, the numerator is a polynomial x cubed plus 1, and the denominator is a polynomial x squared. So to find a vertical asymptote in a rational function, the first thing you do is determine what value a will cause the function to be undefined, or in other words, the denominator to be equal to 0. Jen, what is the vertical asymptote?
Okay, so since the denominator has to be 0, we go ahead and set our denominator equal to 0. So when you set x squared is equal to 0, the only solution is 0.
Are there any others?
No.
Cool. All right, so then secondly, the question asks us to find the horizontal asymptotes. Jen, what's a horizontal asymptote?
Well, a horizontal asymptote is defined as you take your limit of your function as x goes to infinity, then your function goes to some point, we'll call it L.
Also, for some pre-cal students, if you decide to take pre-cal when you get to UT, a lot of times they'll also be called the end behavior, or the long run behavior. So just kind of some nomenclature to sift through. So in this case, we look here and see that, okay, well, if I decide to take the limit as x approaches infinity of this function, what's going to happen is my numerator is much larger than my denominator. This brings up our tricks for horizontal asymptotes. The tricks are, if the numerator is if the numerator is larger than the denominator, the limit as x approaches infinity will approach infinity. Therefore, we don't have a horizontal asymptote. What would happen if the power in the numerator was equal to that of the denominator, Jen?
If the highest power in the denominator was equal to the highest power in the numerator, then your horizontal asymptote would be the ratio of the coefficients. So, okay, for example, say we had 2x over 1 minus x. And that would look like this. Then our highest what is it called, David?
Power.
Our highest power is 1 on the top, and our highest power is 1 on the bottom. And so your coefficient on the top is 2, and your coefficient on the bottom is -1. So you have 2 over -1, so your horizontal asymptote would be at y equals -2.
Cool. And then lastly, our last thing for this is if the denominator's power is larger than that of the numerator's power. And in this case, if that were to happen, your horizontal asymptote would be the line y equals 0.
Mm-hmm.
So we look here in our case and we see, okay, well the power of the numerator is 3. The power in the denominator is 2. And we see that the numerator is greater than that of the denominator. So therefore, the horizontal asymptote in this case would be non-existent. We don't have one. Cool. So what would happen actually, Jen, in this case, since we have the power is actually greater than the numerator by degree 1?
Since it's only a difference of degree 1 with the higher power on the top, then that would mean we have a slant asymptote.
Cool. So a slant asymptote on a graph, basically what it looks like is it looks exactly like a line, but it's an asymptote. So we look here and say, okay, well, there's an asymptote. So a lot of behavior for these asymptotes will allow the function to follow the line. And that's it. So in this case, we see here that this is probably a slant asymptote. There are 2 ways that we can try to figure this out. And the first way is just to see if there's any way we can break up the function. Well, we see here that there's multiple parts on top, and there's 1 on bottom. So when we have this, what we can do is just say, okay, well, I can take the x cubed function and the x squared function, I can divide them. So in this case, what we would have is x cubed divided by x squared plus 1 over x squared. Once we've broken up this function, we can see here that this x squared and this x cubed can cancel or reduce. And when they reduce, we have x plus 1 over x squared. So what happened here is now we have x plus some fraction. Now, x itself is what's our slant asymptote. So the slant asymptote of this function is y is equal to x. Now, that's one way of doing it. It may not always be as easy to manipulate the function and break it up like this. So we do another method. And what's the other method, Jen?
Oh, long division. Oh, okay. If you have more than one term on the bottom, say if you had, the top of our function is x cubed plus 1. So if you had x cubed plus 1 over, say, x squared plus x,
cool.
Then you would have to use long division.
So what long division is it's basically doing division as you would with numbers, okay? The way that I remember what happens is, so you have a division bar, right? So the way that I remember what goes inside the division bar is the simple phrase, the top dog gets the house. So basically, the one on top is x cubed plus 1. Therefore, it's going to go inside my division bar. And then x squared plus x is outside. So this is how it broke up. So now, what you do is you ask yourself, okay, what can I multiply by x squared in order to get x cubed? Jen?
X.
Cool. So what I do is I put an x there. So what I do is I distribute it. So I distribute it, I'd say, okay, x, I multiply it with x squared. When I multiply two bases, what do I do with their exponents, Jen?
Oh, you add their exponents.
Cool, so I'll have x cubed. So now, not only do I do it to the x squared, but I also do it to the x. So x cubed plus x squared, okay? So that's what I have here. And then what I'm going to do is I'm going to subtract the bottom line from the top line, okay? When I do this, I see that, okay, well, I don't have an x squared in my top line, okay? So what I do is just subtract them. Since there's none, I'm left over with a negative x squared. So what had happened was that x cubed actually canceled from line 1 to line 2. And I'm left over with a negative x squared. Cool. So then I say, okay, now what do I multiply by x squared to get negative x squared? Jen?
What? Oh, I was just thinking, don't forget to bring down your 1.
I'm going to bring down my 1, of course. So plus 1.
Okay, what was your question?
So what do I multiply by x squared to get negative x squared?
You multiply by negative 1.
Okay, so I put a minus 1 on top. So when I do that, okay, I'm going to multiply the x squared by negative 1, so negative x squared. Then I multiply x by negative 1 to get negative x, or negative x. Mm-hmm. Then I'm again subtract the bottom line from the top line, so I put a minus sign, right? And when I do that, the x squareds cancel. Then I'm left with positive x plus 1. Cool. That's what I'm left over. Now, Jen, is there anything I can multiply x squared by to get x?
No.
No, there's nothing. So this is like what we have when we're dividing numbers. This is our remainder. What you do is you take the remainder and you divide it by what's called the divisor. The divisor in this case is x squared plus x. So what we're left with is x minus 1 plus x plus 1 over x squared plus x, right? Is there anything else we could do, Jen?
Nope.
Cool. So that's us long dividing. So in this case, our slant asymptote will be defined as y is equal to x minus 1. Cool. All right, so what's the next question asked for?
That's it. We just need to find those 3 things.
So we found them, and that's the answer to the question of the day.
And you grab them.
Bye.